This is static analysis of Python modules using GCC, and Dave Malcolm works at Red Hat. He works on Python core. Give it up for Dave.
Thanks. Cool. Thanks for coming. This is an extreme talk, and experienced as well, so I may have to go very, very quickly. I'm going to assume that you know Python, obviously, and you have some familiarity with C or C++. Hopefully you've looked at some point at a C extension module for Python. Maybe you auto-generated it using Cython, maybe using Swig, or maybe you hand-wrote it, or maybe you've had to step through and debug one. So I'm going to be talking about the bugs that typically occur in C extension modules for Python, which kind of motivates things. Then look at some work that I've done to make the insides of GCC, the GNU compiler, be hackable using Python. And then how I've used that work to add new compilation warnings to GCC to detect when you get, for example, reference counting bugs in C extension modules. And then I've been using that work to do a lot of large-scale analysis to try and basically fix all the reference counting bugs in all Python extension modules, because yay, for big ambition. And so the code is all free software or open source, the GPL v3 license or later, and it's at fedorahosted.org/GCC Python plugin, if anyone wants to follow along. And so let's talk about the C extension API for Python. I really like it. It's a great API for wrapping C and C++ libraries. You can use it to use Python to glue together code that you already have. Historically, it's also been used for speed, where people have taken the inner loops of Python code and re-implemented it in C. But thankfully, that's happening less now that PyPy is in the ascendancy. So if you want speed, use PyPy. Now, it's a nice API, but unfortunately, it's very easy to get certain things wrong. And when you do, you can introduce crashes of the interpreter, where it will segfault on you, or introduce memory leaks. I had a go at writing the world's worst C extension module for Python. Now, if anyone here hasn't used the C extension module for Python before, please do not use this as a model of what to do. I've deliberately made as many mistakes as I could while still creating code that compiles without warnings in a regular C compiler and looks like convincing enough to fool someone who doesn't know what they're doing that the code is correct, but it's actually full of bugs. And so I guess the quiz is, how many bugs can you see in the code that follows? So let's create a new Python method in C we'll call buggy list of random integers, although they'll actually be random longs because this is Python 3, but you'll see that in the next slide. We declare it, it takes self and some args, it returns another PyObject star. We declare some variables, some temporaries, and a long, count, and I value. And at line 8, we call into pyarg parse tuple, which takes the argument tuple that we were passed in, and it uses a format string and some variable length arguments, which is a C idiom, and parses out the I code there means we're expecting a single argument that we can, a single integer argument that will store away in the address we're passed in, which is the address of count, the local long variable at line 6. So if we get in a single GCC, the GNU compiler, be hackable using Python, and then how I've used that work to add new compilation warnings to GCC to detect when you get, for example, reference counting bugs in C extension modules. And then I've been using that work to do a lot of large-scale analysis to try and basically fix all the reference counting bugs in all Python extension modules, because yay, for big ambition. And so the code is all free software or open source, the GPL v3 license or later, and it's at fedorahosted.org/GCC Python plugin, if anyone wants to follow along. And so let's talk about the C extension API for Python. I really like it. It's a great API for wrapping C and C++ libraries. You can use it to use Python to glue together code that you already have. Historically, it's also been used for speed, where people have taken the inner loops of Python code and re-implemented it in C. But thankfully, that's happening less now that PyPy is in the ascendancy. So if you want speed, use PyPy. Now, it's a nice API, but unfortunately, it's very easy to get certain things wrong. And when you do, you can introduce crashes of the interpreter, where it will segfault on you, or introduce memory leaks. I had a go at writing the world's worst C extension module for Python. Now, if anyone here hasn't used the C extension module for Python before, please do not use this as a model of what to do. I've deliberately made as many mistakes as I could while still creating code that compiles without warnings in a regular C compiler and looks like convincing enough to fool someone who doesn't know what they're doing that the code is correct. But it's actually full of bugs. And so I guess the quiz is how many bugs can you see in the code that follows? So let's create a new Python method in C we'll call buggy list of random integers. Although they'll actually be random longs because this is Python 3, but you'll see that in the next slide. We declare it, it takes self and some args, it returns another PyObject star. We declare some variables, some temporaries, and a long, count, and I value. And at line 8, we call into pyarg parse tuple, which takes the argument tuple that we were passed in, and it uses a format string and some variable length arguments, which is a C idiom, and parses out the I code there means we're expecting a single argument that we can, a single integer argument that will store away in the address we're passed in, which is the address of count, the local long variable at line 6. So if we get in a single so we'll use pylist new with 0 to create a new empty list and store that in list. And then at line 15, we'll iterate up from 0 up to the argument that was passed in before. And we'll and again, I really hope that anyone who's used the CPython extension API at this point is feeling like they want to claw their eyes out in horror at the awfulness of this code. This is not an example of how to do it. So I feel kind of bad saying that this is what we're doing because I'll have to explain all the bugs in the next few slides. So we'll make a py-long object at line 16 inside the loop, py-long from long, use random, the C function, to create a random value. We'll make item, pylist append the list, an item, append that new item to the end of the list, and loop, and eventually return the new list. So how many bugs can you see in this code? I count 5. I don't know if everyone can, I'll explain the bugs that I can see in here. So what could possibly go wrong? Well, first of all, pyarg parse tuple, it takes a format string and a variable number of arguments, so the C compiler has no way of doing the type checking to compare that the format string that describes those types actually matches the types that are passed in. Now, we said I, and that means it's a C int variable. And on this laptop, a C int variable is 4 bytes in size. And so it extracts an int and as a 4-byte int, signed int, and it tries to store it in the addressor into count, which is declared at line 6 as a long. And on this laptop, a long is 8 bytes in size. So we have this 8-byte value on the stack, of which we've written pyarg parse tuple writes a 4-byte value into 4 of the bytes of that, but there's also another 4 bytes worth of bits that are ones and zeros, and hopefully, and they haven't been initialized. Now, they might be zeros, in which case the code will work, but every now and again they might not be, in which case count will have this wildly wrong value that doesn't at all relate to the value you might hope. And so you might your code might work fine for a while, and then you might suddenly get bizarrely wrong, massive, huge lists that kill the interpreter when the code is run because it's just huge in memory. There's also, it's not doing any error checking at all. All of these, there are 3 API entry points here on this slide, and all of these entry points can fail returning, well, some of them return null, some of them return an integer return code, if there's not enough memory. So in line 13, if there's not enough memory to create the new empty list that PyList new wants to create, it'll set a memory error exception on the thread's state and return a null back. And if we then go into the list at line 17, well, if you call PyList append with a null as the first argument, that'll immediately cause a segmentation fault of CPython, and which would be bad. You would immediately crash the interpreter. And the other API calls can fail. Pylong from long could fail if there's not enough memory. And so inside the loop, we try and create one. It could return null, so it's setting a memory error. And then we try and append it. Now, in this case, if the second argument is null, it actually doesn't crash CPython. And how many people know which API calls and which arguments exactly can accept null and which can't? I don't think anyone does. And finally, PyList append itself can fail, because it may need to grow the internal buffer of the list, and that could require a memory allocation. And so that could fail, and it will return -1, and we're not checking for that. And at that point, well, it won't crash the interpreter, but you might have asked for a list that was length 100, and you only get a list of length 5, and you're getting the wrong result. And I guess the question is, do you prefer to have the program crash on you, or do you prefer an incorrect result suddenly happening where you weren't checking for it? Interesting philosophical question. So that's 4 problems, but really for me the big problem, I'm always finding myself having to track down are reference count problems. Python objects have, at least CPython objects, have a reference count at the top of them, which represents how many pointers are there in the memory of this process that point at me, so that when the last reference to me goes away, when that reference count hits 0, it can be deallocated. Now, so if that reference count value gets out of sync with the actual pointers in the program, bad things happen. If it's too high, you'll have a memory leak, and the object will become immortal and will never be cleaned up. If it's too low, the object will be deallocated too early, and you may well then have random pointer corruption, and it'll probably crash. And both of those are bad for different reasons. And in fact, a memory leak of just a Python, you might think, well, it's just a single Python object, which is variable size, but it's probably less than 100 bytes in size. But unfortunately, because CPython has an optimized memory allocator, where small objects are allocated out of pools in these 256K arenas, if you have an immortal object for the lifetime of the process, well, that whole arena has now become immortal, and that whole 256K block will never be returned to the system whilst this process is alive. So if you have a few of these, or many of them, well, yeah, you can potentially have loads of these scattered, and your process can become very, very big very quickly, and it's not getting any smaller. So this is bad. And I got really sick of tracking down reference counting bugs. I've tracked far too many of them down, and I thought, this is C, it's a compiled language, surely can we automate this? And I set a goal, okay, for the next release, I work on the Fedora project, the Fedora distribution of Linux. There are 370 packages that link against libpython 2.7. Can I somehow automate detection of all these bugs and basically make sure that just kill this problem once and for all, automate the detection of this, make the compiler detect it, and not have to do all of this by hand. So I started looking at automated code analysis, and there are a few areas of things in this space. There's the LLVM compiler project has a very nice tool called the CLang Analyzer. And it generates really nice graphical error reports for a particular set of coding errors in C. But unfortunately, it only handles C, as far as I know, C and Objective-C. And my code base there's a lot of C, but there's also a lot of C++. There's some Fortran, and there's all kinds of exciting other stuff. And so that's kind of not viable. There's Sparse, which is a static analyzer that was written for the Linux kernel. Again, that only handles C. There's SIL, which is written in OCaml. A colleague of mine used it to verify correct acquisition and releases of mutexes within libvirt, which is a virtualization library we created. But again, only C. Cochinelle, another OCaml tool. I was able to use this a couple of years ago to actually write type checking for PyArg parse tuple. And it's kind of cool, you can auto-generate patches rather than just find the bugs. But unfortunately, it still only handles C code. And there are also some libraries, Python libraries out there that can parse C. I don't know of any that can parse C++. And there's also proprietary tools, but that's a non-starter for me in the Fedora project. Our whole tool chain is free software, open source. So increasingly, I found myself looking at GCC, because all our code is going through GCC already. There's a parser in that, and it has recently gained a plugin interface. So I thought, well, maybe I can write a GCC plugin to detect reference counting bugs. But unfortunately, that would need to be written in C. And I don't really like, there's enough buggy C code in the world already. So I created a bit more buggy C code, but what I did was I thought, well, okay, rather than directly write the code I need, what I can do is embed Python into GCC as a plugin, and then I can write the new static analysis I need in Python, and basically massively increase the hackability of GCC, expose all the internal representation of code so that you can get at it from Python. And partly this was inspired by colleagues of mine who added Python scripting to GDB, the GNU debugger, which I gave a couple of talks about at Pycon last year. And I feel that that's been really, really successful in that we've managed to do all kinds of things in the debugger, like adding CPython support that's in the CPython source tree into the debugger. So I thought, well, let's do that for the compiler as well. So I looked at the tutorial for here's how to write a Hello World GCC plugin, and I looked at the tutorial for here's how to embed Python into an app, and I kind of introduced them to each other, and very quickly had a working GCC plugin that ran the Python interpreter. So you see at line 6, this is the C Python API call for run this fragment of Python code. Let's print the time. And so you run GCC with the new plugin, test.c, compile it, and lo and behold, you have Python code running inside the compiler doing stuff. And generalized it so the Python code isn't hard-coded as a variable, it's actually taking in a script. And yay, we can run arbitrary Python scripts as our code compiles. And I had great fun with this. I was able to embed Django inside GCC so that the code would, you could compile some C++ code, then stop, and then serve HTTP over a port. Which is fun, and thank you. But actually not very useful because what you really want is the internal representation of the code being compiled, and to expose that as Python objects and classes, so that the script can actually look at that rather than just be, hey, I want to serve something. Hey, I've got a process, I'll be in there. So I looked at the insides of GCC. Now GCC is kind of an interesting challenge from an embedding Python perspective, because it's 1 million lines of C code, it's 25 years old, and it's rather, as I said, baroque in this, which is a euphemism. It very heavily uses the C preprocessor. There are macros for everything. It has several implementations of inheritance in C that are different from each other. And it has macros everywhere for expressing how GCC's garbage collector works, littered everywhere. Originally, I tried using Cython, and so I really like Cython. It's my kind of my favorite solution for generating C extension modules. But unfortunately, GCC was just a bit too gnarly for that. So I wrote my own code generator, which is a fairly simple bit of Python code to generate C code. And then I used that to auto-generate C code for all the different aspects of GCC that I needed to wrap. So let's talk about what GCC's internals look like then from Python. So if you remember the buggy C code that I began with all the problems, it goes into the GCC and is compiled, and the characters of the source code get turned into a tree-like representation that then gets turned into a representation that is called Gimple, which is for historical reasons. And this is a very simplified set of expressions and it creates what's called a control flow graph, containing statements in this simplified representation with edges connecting the control flow graph, expressing the control within the function, this is basically compiler 101. And hopefully, I'm grossly oversimplifying things, but that's what's going on. So let's create a new compilation pass for GCC in Python. So we import GCC, which is where all the API is. And I've done it, it's all objects and classes. So to create a new compilation class, you subclass, in this case, gcc.gimpl pass, because it's operating on the gimpl representation. And every pass has an execute method, and this will be called once per function in the code being compiled. And that it'll be called, fun will be passed in as a gcc.function, wrapping the C code function that we saw before. And then here, let's just print some stuff. We'll print the function's declaration's name, and then let's loop through the basic blocks, the function's CFG's basic blocks, and we get a series of gcc.basic block back. So you see how I've created what I hope is a pretty Pythonic API to what really isn't internally. And so it's all attributes and objects and stuff. And let's print the block's index. And then where are we? We're at line 13. If it's got gimpl statements, let's iterate through them. We'll print the repr, we'll print the stringification, and then let's look at the successor edges of control flow leading out from the block and print where they go to. So we've created a new pass as a class with an execute method. We have to instantiate it, giving it a name, and then adding that instance of the pass into the big tree of GCC's pre-existing passes. We'll do it after the control flow graph is the CFG pass, which is immediately after GCC builds control flow graphs for the C or C++ code. Top tip, don't call your pass because then you say pass equals and Python says, no, that's a reserved word. So you do GCC with Python, dump gimpl.py, that's the name of our script, and then you just pass in the regular GCC compilation flags. So it's a Python extension module, so we pass in that. And so here's the code we're compiling. And then the script outputs, well, here's the name of the function. We've got a block and some blocks. And at line 6, there's the gcc.gimpl call. So we have an instance of a gimpl statement representing a function call. You can see at line 7, the stringification of it says, yeah, we're calling parg-parse tuple, and we're going to store the result in a temporary. So GCC has introduced a temporary to handle that. And then there's a gcc.gimpl cond representing a conditional, which you see on line 9, it represents the if that temporary is 0, and then we either go to one edge or the other based on that conditional. And so you see how there's a whole bunch of Python objects and classes representing the insides of the function. But that's lots of text. So we can run, this is Python, we can just run a different script. So for example, show gimpl.py. And it generates, and that basically walks over the internal representation and puts it into GraphViz, and you can see the actual basic blocks and the edges between them. And zooming in somewhat, there's one of them. Within one, this particular visualization prints the source code on the left-hand side interleaved with the gimpl representation on the right-hand side. And the edges have little annotations based on how the edges are annotated by GCC. And there are lots of optimization passes, and there are actually several different internal representations. And I've wrapped much of this in Python. So if you're more interested in the low-level register layouts, well, maybe actually, if you want to help work on this, I'm having an open space over there at 7 tonight. But yeah, there's a whole slew of things that you can now poke at from Python inside the compiler. So where are we? Yeah, we can now have the ability to create new GCC warnings. There's a gcc.warning method where we can add new compiler warnings. So people have done this. Actually, these are all my colleagues of mine at Red Hat. A colleague has created 2 new compiler warnings specifically for GDB. Because we can now add a compiler warning, it's 50 lines of Python. It massively simplifies hacking on GCC, and they have a particular patterns in their source code that they know they always screw up. Like, here are the standard mistakes we make with this particular API. Thanks. So let's add a compiler warning for it. It's only a few dozen lines of Python code, or maybe even less. And another colleague of mine wrote an analysis script, so when compiling LibreOffice, which is a very large body of C++ code, to detect a particular pattern and gathered the results. So, and again, this is Python. You could slurp the results into a relational database, or so again, you can have a web front end to things, which is a whole new type of compiler front end, which is a bad pun for the compiler geeks in the room. And someone else, another colleague, is, this is my favorite, is trying to port Emacs from its own eLisp variant of Lisp to Common Lisp. And in order to do that, he's written, there's a lot of C code within Emacs. And he's basically written a Python script that, as the C code has been compiled, ports that C code to Lisp, which appeals to my inner geek. So where are we? I've spoken about the bugs at the beginning that typically occur in C Python extension modules. And then I've spoken about all the work I've done to make GCC more hackable from Python. So what this is all building towards is I've built a static analysis tool, which is CPyChecker, which detects those bugs and issues new compiler warnings about them. And it's about 10,000 lines of Python code. It lives in the same source tree for now as the main the plugin. And again, this is at fedorahosted.org/GCC Python plugin. It's all free software or open source. So let's try it on our buggy example code. So it's GCC with CPyChecker, which is just a simple harness script that adds the necessary compile flags to GCC. There's not really no magic there, or no extra magic. And compiler extension. And look, and it's saying we have a new compiler warning. Warning, mismatching type in the call to parse tuple. We had a format code I. The argument corresponding for that format code is a long int star, 64-bit, but we were expecting an int star, 32-bit. So that's telling you, that's added type safety to parse tuple. And then the next warning, it will detect the reference count leak on the item within the, within the loop. And it'll tell us, well, we were expecting the reference count to be this value because, and it's tracking, well, what are the pointers that are pointing to this? And what is the value of the reference count? And when it notes at the end of the function there's a mismatch, it warns you about it based on a particular path, the various different paths through the function. And there's many lines of textual output describing that. But what it'll also do is generate, because I got sick of reading the text reports, is generate an HTML report describing this. So here's what it looks like. It shows, so here's the function call, and you can see the little annotation there saying, so we're considering the case when pyarg parse tuple succeeds. We take the false path following the arrow past the error handling suite. We're at pylist new, and we're considering the case when pylist new succeeds, and then we go to the loop. Now the loop, first of all, we consider the case where count is in the range 1 up to the maximum signed int value, and we take the true path, which is the right-handmost arrow. And unfortunately, this is kind of, definitely this visualization could use work, but hey, this is Python code that is generating HTML. So how many people in this room know how to dynamically generate HTML from Python? Hopefully quite a few. So anyway, so it's very hackable, and I would love patches to improve the visualization. So yeah, we go down, follow that right arrow to line 17, where we call the pylon from long, and it says, well, we're considering the case where it succeeds, and in bold it says, well, we're considering the pylon object that's allocated here. We append it, and you see the annotation for pylist append. It says, well, the reference count, well, it started at 1 above, and it's now 2, and it's also now referenced by the pylist object's ob item, the 0th element of its ob item. So essentially, every time the reference count changes, or the set of all pointers pointing at it, the object change, it'll emit an annotation telling you about that. So you can try and again, the exact visualization could use some work. Help will be very much appreciated. And there's an open space at 7 tonight. And anyway, we follow the arrows back out round. We go now considering the case where the count is 1. So we bail out of the loop to return list. And here's our warning. The reference count is 1 too high. It doesn't yet tell you, well, you actually needed a decref, but I've added some heuristics for example, when you say return pi none, it'll tell you, did you mean pi return none, which is a macro to fix the ref count. It has some smarts in the reference count model, so it can actually prove where a decref won't cause a deallocation. And there's a lot of work I put in to try and eliminate false positives. So the lack of error checking I spoke about, it detects that. So here's another error report generated by this tool. So again, we consider the case where pi plus tuple succeeds. We go through to the pi list new, but now consider, you see the annotation, when the pi list new call fails. We go into the loop, perhaps, or at least we go into the loop when count is greater than 0. Now, we consider when pi long from long succeeds, and now the pi list append call happens, and it says in red, we're calling pi list append with null as the first argument. And then it has an extra annotation. It's saying, well, pi list append, it invokes pi type on that argument because it uses the pi list check macro. So it's actually saying, well, why is this going to crash? And what I've done is I've actually gone through much of the CPython API, or at least the ones that I keep running, the first part of the long tail, and basically created a description just saying what are the possible outcomes that can happen of each function call, a failure versus a success, and for each one, what is the impact on all reference counts, or any reference counts that may be affected by this, or indeed, does it deallocate memory, and things like that. So how does this work internally? Well, basically it's an interpreter for that GIMPL representation, but it's a form of abstract interpretation, at least as very simple form of that, where rather than having specific values, I track all possible values. And I generate a set, and this is kind of a dumb way of doing it. Mathematically, there are much more sophisticated ways of doing this, but this works well enough. I generate a set of all possible traces of execution through the function. So I have a tree of, here's the initial state, and then what could happen next. And then and record, well, and then eventually, hopefully, the function terminates, and here is everything that happened. And I wave my hands about loop terminate. Well, I'll tell you about loop. Every time, for all loops, I analyze the case where we go 0 times through a loop and 1 time through a loop. And that covers, I hope, reasonably well the resource management issues that we're looking to add detection for. Obviously, it's not mathematically rigorous, but if you want to mathematically determine if, or computationally determine if the thing halts, that's, an interesting problem. And so we have a tree of states with transitions between them, and the transitions can have additional descriptions, like this is the transition of pi list append failing. And within each state within the state tree, there's where are we in the function, and then there's the mapping of here are all the variables we know about, and here are all the storage regions. And for each storage region, there's a class hierarchy representing storage regions on the heap versus storage regions on the stack versus globally allocated. And then for each storage region, there's a mapping saying, well, what are the abstract values in those regions? So essentially, we're modeling L values and R values, and that gives us pointer semantics so that pointers work properly, although a lot of other things don't. Again, patches would be very welcome. So this implements basically a static analysis engine written in Python that's pluggable. So there are various types of abstract value. There's the unknown value where we don't know anything at all about the value, versus there's a concrete value, versus there's a value in a particular range. There's a value pointer to region, which means we know this is a non-null pointer that points at a specific storage region. And I have poisoned values that represent deallocated memory or uninitialized memory. And for each of these different subclasses of value, I have operations like addition, dereferencing, subtraction, comparison. And so, for example, if you try and add a value to an uninitialized value, that'll raise an exception of a particular kind, and that'll bubble up, and the static analysis engine will then turn that into a compile time warning and generate the HTML report that you saw. And it's pluggable, so this part of state kind of represents C and C++'s kind of basic semantics, but you can add additional domain-specific facets of state. So not only is it have I allowed you to hack in Python on GCC, but also you can extend in Python the static analysis engine. And so that right now the only one is a CPython facet, which adds what is the status of exception, the thread local exception state. Has an exception been raised? Do we own the GIL or not? And it adds some new abstract value types specifically for handling the reference count semantics, along with all that detailed information I mentioned before about how the CPython API works. For example, does this function return a new ref versus a borrowed ref? Does this function steal a reference to argument number 3? Or, and so on and so forth. And again, looking there in the source tree. And unfortunately, it's a procedural description rather than a declarative one. So we have an impl, for example, pi mapping size is one entry point. It's rather word wrapped, line wrapped, but we have some metadata. And then let's at line 9, we'll have a transition representing success of this call, where we'll make a transition representing an assignment to the left-hand side of an unknown value of the appropriate type, and we'll annotate it with a description saying this is pi mapping size succeeding. And then at line 14, let's create the failure transition, where we say, let's make an assignment to the left-hand side of the call of the concrete value -1, because that's what it returns when it fails. And again, annotate that transition with saying this is that function's metadata failing. But we can also say at line 20, the failure transition's destination states CPython facet. We can say, well, there's a type error has been set when that occurs. And then at line 23, we'll say, well, we return here are the two transitions. We have a success transition and this failure transition. And that's how I've implemented a pluggability for describing an API. Fortunately, it's procedure. I kind of wish now it was declarative. Maybe there's a way of fixing that. Hey, Lisp, yeah, it's not going to Lisp. And so, for example, that's how the description of failure happens for PyList append. In line 5, I'm saying, well, raise if we get a null pointer argument for argument 0 for the pointer. But we can say why. And that can then get turned into a description to the user of, well, we're going to use PyList check, which is a macro that has PyType, so we're going to dereference the ob type field. So if it's null, that dereference null's ob type will segfault. But we're at line 11, we can say for the other argument, if it's a null pointer, we can create a state and transition to it, returning -1, and setting an exception, in fact. So basically, I've built a general purpose static analysis engine in Python running inside GCC. And then I decided, okay, let's run it on, say there are about 360, 370 packages in the Fedora 17 is our next release. And I try to automate as much as possible running it. Now, it's not fully automated yet, unfortunately, because the tool still has bugs in it. It's kind of alpha quality. And so, but I've automated lots of the process. And so I fired a lot of bugs, and some of them have been fixed. I'll show you some of those in a bit. And until there was a bug where it didn't properly support C++, which I fixed on the flight here. So I hope to rerun the analysis on all the C++ code when I get a moment. Swig and Python code and other kinds of auto-generated code give the checker a real workout. And I've got it to be fairly silent on Python code. Swig, it's still pretty noisy, and I don't really trust Swig enough that I want to deal into that further and actually try and find if there are real bugs there. And yeah, and a lot of them I'm still dealing with tracebacks in my code and a whole bunch of issues, because there's some of these projects are built with Makefiles, and some are dist utils, one's the Linux kernel, and so on and so forth. So there's a whole interesting long tail, it's not so much a long tail as the long body, unfortunately, at this point with those percentages. But yeah, and so that's kind of where I'm at now. So then there's my tracker bug. So here's an example, Bluefish, which is, I wrote a script to take all of those HTML error reports and create a summary and kind of triaged into most severe through least severe categories. So for example, this is an HTML editor that's part of the GNOME desktop, or at least I think I'm not sure actually, I may be out of date there. And so there were a couple of reference count leaks it found in under standard operation. It also found within module initialization, there's you're not increfing something. And to some extent, everyone gets module initialization wrong, or at least no one really seems to care, because it only gets called once. And if you're not increfing the singleton representing the integer 0, who really cares? I'm not quite sure. Maybe Pypy care. Okay, maybe yeah. And then there's the category of there's a segfault in error handling, which normally actually means there isn't any error handling. And that's where, and that one there was a. I think it assumed a call would succeed and then dereferenced the result. So here's one of the reference count leaks from from Bluefish. At line 161 that's highlighted, it calls PyObjectCall method to invoke a method, stores the result in pcaret placeholder. So it's considering the case where that succeeded, and that gives you a new reference that this code owns. And then it goes on to line 167 because it's non-null. And then does something with it, and I got a horrible feeling actually looking at that it's returning the insides of it. So that's actually a bug still. But yeah, it detects that there's no decref going on there, that code is going to leak that string, the string that's returned by that method call every time that this C code is called. Also, you notice it says found one similar trace to this, with bad pluralization. And there's actually a deduplication engine which takes all the tree of traces and the things through it and tries to reduce the amount of spam that's generated. So here's another example from CMU Sphinx, which is a voice recognition piece of software that has Python bindings. And so within this particular method, getHypothesis, which presumably is taking a sound sample and saying, well, what do we think the person might be saying? At least that's my guess of what it is. So there's a big body of code that I've snipped, but essentially you have code that has two references that are owned to hipstr-obj and hipseg-obj, and that right at the very end it calls pybuildValue 00 on it. Now, I've actually, and within, the nice thing about having the scriptable static analysis engine is I've taught it what are the reference count implications of all of the different format codes of pybuildValue. So, and O adds a new reference, so it constructs a two-tuple of those two things, but adding new references for the two-tuple, but it doesn't take ownership of the existing references. So both of those leak every time through. And again, that's now been fixed by CMU Sphinx, the upstream project, based on my bug report. Here's an example from RPM, where, yeah, maybe I shouldn't show all RPM bugs, from RPM's Python bindings. At line, so there's a load of logic here for a RPM FD object representing a wrapped file descriptor. Don't ask. And in some error handling that begins at line 31. At line 32, we decref FDO. And then at line 33, we set an exception. But unfortunately, at line 35, we actually dereference FDO again after we decrefted above. And the checker actually found this, saying reading from deallocated memory based on that sequence of operations. So, yeah, as I said, there's some limitations. So it only complains about crashes, and it only complains about what it knows how to complain about. It can't read your mind. So, for example, so it gets many of the bugs that I mentioned before at the beginning of the talk, but but for the case where the list is just too short, well, it has no way of knowing that you meant to write code that worked that way. Just, so you can't complain about that. Also, as I said, the loop termination is a bit of, it's a heuristic. That's, I guess, my euphemism for that. And also, yeah, Cython and Swig, well, I'm working on fixing that. So yeah, so what have I've told you about, we gave a tour of the bugs that typically occur in C Python extension code. And then I described the GCC plugin I've written that embeds Python inside GCC and thus lets you very easily hack on the insides of the compiler. And then the code that I've used to build a general purpose static analysis tool in Python running inside GCC. And finally, the pluggability and how I've then used that to build a static analysis engine for reference counting. And so there's a whole bunch of different places where this is actually pluggable and hackable from Python. And also then how I've used it on all this real-world code. And I want to give a shout-out to my employer, Red Hat, for paying me to work on this and give away all the code. And we're hiring, and we have an install here as well, actually. So if you want to work on Python for Red Hat, that's cool. Please, if you have extension code, try the checker on it. I've got and tell me about, if you found bugs with it, that's great. If you ran into false positives, let's try and fix that, or at least minimize the damage. Some instructions on how to do that are on screen. And if you've got ideas for other compiler hacks using this, now that we can hack on the compiler using Python, that'd be great. And I'm running an open space here or over there at 7 o'clock tonight. So, and that's my talk. So thanks for listening. All right, thanks.